right? We go through this transition, n equals 236 to n equals 235. They want to find the wavelength of light that's given off. It's going to be kind of a weird wavelength, right? So for the Balmer series, 1 over wavelength equals Rydberg's constant times 1 over my final quantum level squared minus 1 over my initial quantum level squared. And as we can see, like, because both of these are going to be really, really, really small numbers, right? I'm squaring 236 and I'm 1 divided by that giant number. It's going to be such a small number. There's not going to be much of a change between these two energy levels. So 1 over wavelength equals 1.097 e to the 7. Final is 235 squared minus 1 over 236 squared. Right, I'm honestly curious if we just ignore. I think this is going to be so small, we can honestly just ignore that and just use this equation, right? This relationship right here to find what the wavelength is going to be. But we'll go for the calculation to see. Let's see. 1 divided by 235 squared minus 1 divided by 236 squared. Yeah, so I get 1 over wavelength equals 1.097 e to the 7 meters times 1.53 e to the negative 7. So multiply those two together. I get 1 over wavelength equals 1.67 0.68. So multiply both sides by my wavelength. And I get 1 equals 1.68 times wavelength. Divide both sides by the 1.68 to get wavelength by itself. Gonna get a weird wavelength of 0.595 meters. And then what do they ask for? Scientists have detected, blah, 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 calculate the wavelength in nanometers. So, all right, we've got the wavelength in meters. Our wavelength is 0.5 meter, right? Very low energy, not much of a transition at all. But then the last step, convert meters to nanometers. So, okay, I've got 0.959 meters, and I know in 1 meter, right, I've got 1 billion nanometers. So in this case, I'm multiplying. So we would get what? We get 5.95 e to the 8th nanometers, I hope. For that, so not much of an energy transition because of those two large quantum numbers. And the higher the quantum number, right, the closer and closer they get in energy. It's really the smaller quantum numbers result in a bigger change in energy. That's all we had to do for question 35, Harrison.